Here is the introduction to section 4.4. Only an introduction for section 4.4. No activity. I think this should be enough to allow you to do the homework that's assigned in the textbook. Okay, so we've seen that the definite integral represents a signed area. So if I have some function that looks like this, and I'm integrating from a to b, then as the integral views things, this piece of area would be positive, this piece of area would be negative, and this piece of area would be positive. Okay, so the velocity of a particle in feet per second is given by t squared plus 3t minus 4. What does the integral from 0 to 3 of v of t represent? Okay, let's think about it. First, let's just evaluate it. So the integral from 0 to 3 of t squared plus 3t minus 4, and we're integrating with respect to time. So that is, let's see, integral of t squared, antiderivative is t cubed over 3, plus the antiderivative of 3t is 3/2 t squared, minus 4t, and we're evaluating from 0 to 3. Okay, so let's see, we evaluate this thing at 3. We get 3 cubed divided by 3. Well, that's just 3 squared. So that's 9. We get 3 squared is 9 times 3 is 27. So that's 27 divided by 2 minus 3 times 4 is 12. And every term here has a t, so when we put in 0, we're going to get 0. So what do we get? 9 plus 27 halves, so that's 13 and a half. So 13 and a half minus 12 is 1 and a half, so we get 10 and a half. What would the units on this be? I don't know. Let's learn something about this function. So let's see. We're looking from 0 to 3. So let's draw this picture. At 0, the output of this function is negative 4. Let's see, t squared, can we factor this thing? V of t is t, let's see, plus 4, t minus 1, so it hits the x-axis at 1. It's a parabola, it hits the x-axis at 1, and we're looking all the way over to 3. At 3, where are we at? 9 plus 9 is 18, so we're all the way up to 14. So it's growing pretty quickly. I don't know where its vertex is, right? I know it hits the x-axis at negative 4 also, so its vertex is down there, is over here somewhere to the left, but it's doing, this is not to scale, so let me draw it and then fix the drawing. So this is a piece of a parabola. It's crossing the x-axis here at 1, and this was the value at 3. Sorry. Not my best drawing ever, but we'll make it at least represent what's going on here. Okay, it's increasing during this time. It starts at 0, negative 4, it gets up to 3, 14, I think we decided. But anyway, let's think about it. What are the units here? The units here on this axis are t, and the units on this axis are feet per second. And so when I multiply those units to find this area, which is treated as negative, and this area, which is treated as positive, the units on this would be feet per second times seconds, which is feet. So that 10 and a half represents a number of feet, but it actually represents not how far this particle has traveled. It represents its displacement, because from 0 to 1 it was traveling backwards, and then it starts going forwards. It went 10 and a half feet further forwards than it did backwards. So it went backwards, then went forwards, and ended 10 and a half feet away from where it started. So this is its displacement. If we wanted to find, how could we find its total distance traveled? Well, the total distance traveled would need to turn this piece into a positive quantity instead of a negative quantity. So we would need to find the opposite of the integral from 0 to 1 of t squared plus 3t minus 4 dt. And we need to add to that then the integral from 1 to 3, because that piece is already positive. And if we do that, then we should get the total distance traveled. So let's see, what does this look like? T cubed over 3, plus 3, oh my goodness. All right, I can do this. Plus 3 halves t squared minus 4t, evaluated first from 0 to 1. We need to hit all of that with a negative, plus that same t cubed over 3 plus 3 halves t squared minus 4t, again evaluated from 0 to 1. Okay, let's see, I put 1 in there. What do I get? I get 1/3 plus 3 halves minus 4. I put 0 in. Whoops, let's fix this one over here. 1 to 3. Put 0 in, I'm going to get 0. So this piece is negative 1/3 plus 3 halves minus 4. And over here, I add to that. I evaluate this thing at 3. I did that above. And evaluating it at 3 above, we got 10.5. 10.5 minus whatever we get when we evaluate this thing at 1, which is 1/3 minus 3 halves plus 4. Let's see, what do we get here? 1/3 plus 3 halves, I guess we got to go to sixths. So that looks like 2 sixths plus 9 sixths, that's 11 sixths. Minus 4 is 24 sixths, so that's negative 13 sixths. So I think we get 13 over 6 here. I'm running out of space, but we can do this. And here, again, let's see, negative, negative, positive. I distributed the negative, so that's good. So that's 2 sixths. And again, this is 9 sixths, so that's negative 11 sixths. Plus 24 is another 13 sixths. And 13 sixths, 10.5. So we get plus 10.5 plus 13 sixths. Let's see, 10.5, 21 halves, 33 sixths. So we get 33 and 13 is 46, and 13 is 59. So assuming my arithmetic was right there, we should get 59 over 6, and that is a quantity of feet. So the total distance traveled is, we take the distance we went backwards, we turn it into positive distance, we add to it that distance that we went forward, and we get that by looking at both pieces of this integral. So the integral of velocity is going to give you displacement if some of that area, if some of that function lives below the x-axis. That distance is treated as negative, so we would have to figure out where our curve crosses the x-axis. In this case was at 1. We can break it up into 2 integrals then, and those 2 integrals, when we multiply the one that's negative by a negative sign, gives us the total distance traveled of our particle. Okay, the only other new idea here in section 4.4 is the idea of an indefinite integral. So up to this point, we've looked at definite integrals. Indefinite integrals, no limits of integration. And all an indefinite integral is asking you to do is to return all the possible antiderivatives of your function. Okay, so how do we do that? Well, we write down the antiderivatives. The antiderivative of 3x squared, let's see, 1 more power, we divide by 3 is x cubed. Antiderivative of 6x is 3x squared. And then we could add any constant to that. And that would be any number there we wanted. We saw this previously in section 3.9, I think. That would be 11 pi. Any number you want. You take the derivative, you're going to get back to 3x squared minus 6x. So this is just a constant. Okay, so that is all a indefinite integral is asking you to do. It's not asking for an area, it's asking for a set of functions whose derivative are the thing you're taking the antiderivative of. It's really saying go ahead and take an antiderivative antiderivative. So the antiderivative of sine is negative cosine. If we want all the antiderivatives, we add a constant. The antiderivative of secant squared is tangent. If we want all the antiderivatives, we add a constant. In this case, we'll do a little bit of work. This is the antiderivative of t squared divided by root t plus t divided by root t. So this is the antiderivative of t to the 3/2 plus t to the 1/2. What do we get? 5/2. 2/5 t to the 5/2 plus we go to the 3/2, so 2/3 t to the 3/2. And if we want all the antiderivatives, we can put any constant we want on the end. Okay, so two ideas are displacement versus distance traveled, which happens by looking at where our functions cross the x-axis and breaking into multiple integrals if needed. And then the other idea is this idea of the indefinite integral, which isn't asking for an area anymore. It's asking for you to return all antiderivatives of the given functions. So you should be able to use that information to go ahead and start the homework. No activity again, no activity for section 4.4. Go ahead and start the homework.